So this is your book's illustration for demonstrating more substituted alkene is more stable. The more alkyl groups bonded to the sp2 carbon, the vinyl carbon, the more stable the alkene. So we have the tetra substituted as the molecule at the left. Then we go to tri, geminal disubstituted, and monosubstituted as the least stable. A transalkene is more stable than a cisalkene, and a cisalkene will actually have relatively the same stability as a geminal alkene. So you can see that the cisalkene is listed at negative 28.6 for the enthalpy. If we go back to our formal side, the geminal disubstituted is listed at negative 28.5. So those have relatively the same energy, and we can make a note of that in our table. Okay. So relative stabilities of alkenes that have two alkyl groups, the cis is approximately equal to the geminal disub. So we can say we are comparing the energy of the cis to the geminal to the trans for all of our disubstituted options. And when we compare these, the trans is the most stable, and the cis and the geminal are about the same. So we're going to go back to reaction coordinate diagrams and what they mean for fast or slow exergonic and endergonic reactions. So going back and remembering from Gen Chem 1 that the greater the activation energy, so this is activation energy, and I think that your book uses the term, they use the G with the transition state symbol with the double cross, but they also use, I think, E sub A, activation energy. And the greater the difference, or the higher the maxima of the graph, the slower the reaction progresses. So a smaller activation energy will occur faster than a larger activation energy. So what we can do is we can say that B is faster than A for comparing the graphs. We can also compare the value for delta G. Is it positive or negative? So we can say that A and B are exergonic, and C and D are endergonic. And that has to do with whether delta G is greater than or less than 0. If delta G is a negative value, it's exergonic. If delta G is a positive value, then it's endergonic. Okay. And both, so we can say that B is faster than A, but I can also say that C is faster than D because the transition state energy is less for C than it is for D. And we're looking at then the value from the energy of the reactant to the absolute maxima of the graph. So, energy of reactant to the max. The difference between these values is the transition state energy. We've already looked at state functions. We can do the same state functions with the transition state that we did with just the general Gibbs free energy, enthalpy, and entropy equations. So you won't have to use this equation. I don't intend to put this on your work, but it is good to look at it. Enthalpy of the transition state minus enthalpy of the reaction of the reactants is equal to the enthalpy of the transition state. So basically what you're doing is you're taking the maximum of the maximum energy given in the graph, and you're subtracting out the energy of the reactants. Okay, we have terms to define the transition state and also the overall reaction. So kinetic stability is indicated by transition state energy. So when we look at kinetic stability, all we are worried about is the transition state. Do not look at the overall energy of the graph. And kinetic stability, we have large kinetic stability, which means that it's going to be immovable or reacts more slowly. So a higher value is a large kinetic stability, while a smaller delta G is a reactant that is kinetically unstable. And remember, kinetics is movement. So if it's kinetically stable, then it has less movement or slower. And the kinetically unstable means that it is moving more or faster movement. Okay, thermodynamic stability, that's where we're talking about the energy of the overall reaction. Delta G overall reaction. And that's where we're taking product minus reactant. And you need to be sure that you have these terms clear in your mind. If delta G is less than 0, then we consider the product thermodynamically stable compared to the reactant. So the product, remember that stability is having a lower energy. So the product has a lower energy than the reactant if delta G is negative. If delta G is positive, the reaction is thermodynamically unstable, or the product is thermodynamically unstable compared to the reactant. So in this case, the reactant molecule is more stable than the product molecule in terms of energy. So the reactant molecule has a lower energy than the product molecule. I want to remind you that the rate of a reaction, what affects the rate of the reaction, this is where we use the Arrhenius equation. A equals, oh, I can't remember the exact equation. Maybe it's later in the PowerPoint. But this is where we have, here we go. K is equal to A times E raised to the power of the negative activation energy over RT. That's basically explaining the rate of a reaction, K, based on the number of collisions per time, A, the fraction of collisions with sufficient energy, which is also part of the A term, and the fraction of collisions with proper orientation. So increasing the concentration increases the rate, increasing the temperature increases the rate. And the reason that increasing the temperature increases the rate is because the number of collisions per unit time will increase. If the number of collisions per unit time increases, then so will the fraction of collisions with proper orientation. And so will the fraction with sufficient energy, because the more collisions you have, the more of those collisions have sufficient energy, and also the more have proper orientation. The rate of a reaction versus the rate constant for a reaction. So remember that rate of a reaction versus rate constant is not the same. We write rate as the rate is equal to the rate constant times concentration. And A refers to frequency and orientation in our Arrhenius equation for rate. And the term of the second term in this equation, the e raised to the negative EA over RT, this is the fraction of collisions with the minimum energy required. You are not going to have to use these equations in your book. I just want you to always keep in mind that whether a reaction occurs and forms a new bond depends on number of collisions per time, fraction with sufficient energy, and fraction with proper orientation. Those are just abstract concepts to keep in mind. Also, please remember that the forward rate is equal to the reverse rate. And what this means is that in your book, they like to give you a reaction energy coordinate diagram. And then when they ask the question about, they'll ask a question and they'll have the names of the product and the reactant, and they'll say, as you move from this to this, is the reaction endothermic or exothermic? And they could be asking you as you go from product to reactant the way that but they're asking about the reverse reaction. So you're looking at the graph and your eyes automatically read the graph from left to right. But the way that they word the question, they're specifically asking you to interpret the graph, reading from right to left. So please be careful in reading our questions that we have on exams and homework. Okay. So forward reaction is equal to reverse reaction. That means that KEQ is equal to the rate of the forward reaction divided by the rate of the reverse reaction, or products over reactants. And again, you're not going to have to do math with these equations. You're going to have to apply the concepts of the equation. Okay. So if KEQ is equal to 1, then B is equal to A, and the rate of the forward and the rate of the reverse reaction are equal, right? If KEQ is less than 1, then the rate of the, if it's less than 1, then the rate of the reverse reaction is greater than the rate of the forward reaction. And reactants are favored because we're going back towards reactants more quickly. If KEQ is greater than 1, then the rate of the forward reaction is greater than the rate of the reverse reaction. So this top value is happening faster than the bottom value. And that means that products are favored over reactants. So those are just things to keep in mind as we move forward.